Good afternoon, guys. This is Professor David J. De Los Reyes, an electrical engineer by profession and a troubleshooter in electronics, hands-on troubleshooting. Okay, let's proceed. My topic this afternoon will be a new topic under length of arcs. This will be polar equations. Okay, let's proceed. My topic for this afternoon, guys, is lesson number 93 on my channel under the topic integral calculus, subtopic length of arcs. The topic for this afternoon under length of arcs, there are actually three variations, okay? We are now through with the Cartesian. We are not through with the parametric. So I will now discuss the third variation under length of arcs. If the given equations are expressed in polar equations, what will be the formula? Okay, so the topic for this afternoon will be length of arcs if the given equation is polar equations. Polar, meaning we are given r as a function of theta. Okay, where theta could be constant or theta could be variable. If theta is constant, okay, there's no problem. It's an easy problem. But if theta will be variable, meaning the right-hand side of the given equation is a complicated thing. It is in terms of trigonometric function. Okay, polar. That will be a variable theta, so the solution will not be easy. So there are two classifications also under r equal to function of theta. If the right-hand side is constant, it's an easy one. If the right-hand side is variable, meaning it's a complicated equation, okay, the problem is not an easy one. Okay, let's proceed. The formulas needed, okay, under length of arcs under polar equations will be, we got number one. This is number one. Differential length of arc equal to the square root of r square dr over differential theta quantity square. If this is theta, this should be differential theta. That is formula number one. Under formula number one, the upper limit is theta 2, the lower limit is theta 1, and we are given r as a function of theta, and theta could be constant or variable. That's formula number one. Formula number two, it was derived from formula number one. Differential length of arc equal to the square root of r square, differential theta over differential r quantity square. If this is r, this is differential r. That's formula number two. Okay? The upper limit will be r2 and the lower limit will be r1. And we are given theta as a function of r, and r here could also be constant or it could be variable. Okay, so these are the two formulas needed under polar equations. We are supposed to be given r as function of theta for case number one, and we are given theta as a function of r for case number two. Okay. The derivation will be on the right hand side, okay, before I will present this figure over here. If we try to get a differential arc on a polar coordinate, it will be something like this. Sorry for that one. This is this triangle here is almost a right triangle, okay. This side here will be r differential theta, and this side here will be differential r, and the hypotenuse will be differential length of arc. Okay. Actually, this is not a perfect right triangle. It is almost a right triangle, right? So, using Pythagorean Theorem over here, the square of the hypotenuse equal to the square of the adjacent side plus the square of the opposite side. ds quantity square equal to dr quantity square plus r differential theta quantity square. I got it from here. Then dividing all terms by differential r quantity square. Differential s quantity square over differential or theta quantity square equal to differential r quantity square over differential theta quantity square. We multiply all terms or we divide all terms by the square of differential theta. Okay? So actually, this will cancel. Okay? So this will be ds over differential theta quantity square. Power 2, take the quotient, then under single power 2 equal to, this cancels out, so this is r square. Power 2, take the quotient, then under same power. Okay, then take the square root. Why take the square root? ds over differential theta equal to the square root of r square plus differential theta over, or differential r rather, differential theta quantity square. And solving for this, we multiply all terms by differential theta. Okay, we multiply. So left hand side, this will cancel out. It is differential arc equal to the square root r square differential theta quantity square times differential theta. It is this. Okay, and the reverse of it, actually we could derive this one by just instead of dividing this by differential theta, we will divide this by differential r. What will come out will be variation number 2. Differential length of arc will be equal to the square root of r square. It is the reverse now. Differential theta over differential r quantity square. If this is r, this should be r. Okay? If this is theta, this should be theta. That's why on first case number 1, the limits are actually theta 1 and theta 2. For case number 2, since we are integrating with respect to r, the limit should be r1 to r2. So I just presented the derivations of the two cases. Okay, let's proceed with the problem. The given problem is an easy problem. Derive the circumference of a circle of radius r using polar equations. Well, we drew the graph. It is supposed to be a circle. 0 angle, 90 degrees or pi over 2. This is pi or 180 degrees. 3 halves pi or 270. 1 complete revolution is 2 pi radians or 360 degrees. And if we try to connect the dots, our graph is supposed to be a circle in which the radius going around is constant. Okay? So this falls under this case here, where r equal to a function of theta, the right hand side will be a constant. So if we try to bring out the solution now, from the relation r equal to a function of theta, for the given problem, r is equal to constant for a circle. All throughout one complete revolution, the radius is not does not vary. So I place it here, r is constant. Or you can place this as just simply capital letter C. Okay, taking the differential of both sides, the differential with respect to theta of r is dr differential theta equal to dr, or the differential with respect to theta of c. Since c is constant, the right hand side will be 0 for a circle. So it's an easy money for a circle. Okay, squaring both sides, dr differential theta quantity square equal to 0 square is still 0. So if we try to go back to case number 1, we follow this one, or this one. D is now will be the square root of r square plus 0. Okay. dr differential r over differential theta quantity square is 0, so this is 0 times differential theta. So what remains inside is just r square, a perfect square. A plus or minus, right? We use a plus because minus, that will be absurd. Differential length of arc for a circle now will be r, the constant radius, times differential theta. To take the total circumference, try to integrate both sides. Right? The integral of ds equal to r, I am following this. The integral from 0 to pi over 2, differential theta, I will place times 4 over here. Okay? The circumference of the circle, we will just take 1/4. Okay? That will be from 0 to pi over 2, then times 4. So that's the significance of this times 4 over here. So S now will be equal to 4r. The integral of differential theta is just theta with the limit from 0 to pi over 2. 4r, quantity pi over 2 minus 0, but this is 0. Right? This 2 here cancel with this is 2. 2 pi r. So S now, or for a circle, I place it at C, circumference, equal to 2 pi r units. Or in terms of, what you call this, diameter, this should be pi d units. Okay? So, for a circle, the derivation is an easy one because the radius of the circle is constant. Okay, but other polar equations, it will be a different story. But whether the problem will be easy or not, if it will fall under case number 1, use this equation number 1. If it will fall under case number 2, use case number 2. Okay, that's it, guys. So that's the so-called derivation of the formula for the circumference of a circle using polar equations. Okay? Because sometimes there are problems that the given equation is in Cartesian, so use your Cartesian method. If it's under parametric, use your parametric equation. If it's under polar, use your polar equation. So this is the polar equation cases. Case number 1, case number 2. Okay, good afternoon, Los Angeles.